Hello, I'm Ruslan Nikolaev from Penn State. In my today's talk, I'm going to present Adelie, a kernel defense mechanism which uses continuous address space layout randomization for Linux drivers. This work is done jointly with Hassan, Nadeem, Cathlyn, and Binoy Ravindran, who are from Virginia Tech. Over the last 2 decades, the number of driver vulnerabilities has increased exponentially for both Linux and Windows. You can see that on this chart, and there are two major problems. First, kernel vulnerabilities are very attractive for an attacker because once the attacker gets to the kernel, the entire system is compromised, and therefore the attacker bypasses all user space mechanisms. The second part is that if we have driver vulnerabilities, that is more likely to actually happen because when each driver is going to be only executed on a subset of systems, therefore not as well tested as it's not going to be as well tested as core or as components. So clearly, driver vulnerabilities is something that an attacker would potentially be attracted to. So in our work, we address control flow attacks. So that historically, control flow attacks imply a buffer overflow attack. So when we effectively substitute return address and substitute the sequence of instructions by hijacking that with our own set of instructions. So now this is not possible on the newer systems which implement the non-executable bit. With the non-executable bit, we no longer can just execute anything from our data page because the data page is going to be marked as non-executable. However, we can still replace the return address, and using some tricks such as finding pieces of existing code and connecting them together, an attacker can effectively replicate the same behavior. And this is what the return-oriented programming or ROP is. So an attacker has to generate a chain of so-called ROP gadgets, and this is what's going to be eventually used. ASLR, address space layout randomization, mitigates traditional ROP. So the idea of ASLR is that each time we choose a random address, therefore even if an attacker calculated addresses for ROP gadgets one time, it's not going to be valid next time, and so on. This is fine for traditional ROP, but more elaborate ROP attacks can sometimes leak this address, then the attacker can observe this address and calculate ROP gadgets specifically for that execution period. So another thing is that kernel ASLR in Linux for x86-64 is also limited. So it's actually only supports KSLR for 32 bits. And the reason for that is because most instruction operands are 32 bits, and therefore absolute addresses are limited to sign extended 32-bit addresses for code and data. So this is unless you change the executable format for Linux, that's what we have currently. So our contributions are: first, we extend KSLR from 32-bit to 64-bit. Second, we implement stack randomization, address encryption, and continuous SLR on Linux modules such that we can protect against more elaborate, such as just-in-time ROP attacks. We have several goals that we achieve. So first, we transform all modules to the 64-bit KSLR model. Second, we also want to increase entropy. Therefore, kernel modules can be any distance apart from each other. we also want to maintain good performance by avoiding costs of copying the code and data during randomization. With respect to security, we protect against code reuse attacks. So that's our goal. So to extend KSLR, we use a preliminary patch, and this preliminary patch converts the Linux kernel from a regular executable to the position independent executable, or PI. The the advantage of PI is that it can be executed anywhere in the 64-bit address space. However, we cannot use PI for kernel modules. And the reason for that is that this module is really limited only to executables, which and the modules are not executables; they are relocatable objects in the Linux kernel. And then you also have to have import, export some symbols, so that becomes more complicated. So we use a more general PIC module for modules, which is similar to shared libraries with global offset and global offset table and procedural linkage table support. So by using PIC and extending every single kernel module to the PIC model, and as well as using this preliminary PI patch for the Linux kernel itself, we can extend KSLR to 64 bits. And the reason for that is because even though the operands are still 32 bits, they are now relative to the instruction pointer. So therefore, we can reside anywhere in the 64-bit address space while avoiding costly absolute address modules such as IMC model large. So compilers rely on the procedural linkage table and global offset table to call external functions and return external addresses. We use this to support multiple mappings to code during ongoing randomization. So in the code, we have a call function, and it's actually calls a special PLT stub. The PLT stub retrieves the absolute 64-bit address from the global offset table to the register and then jumps to this register. So, like in the previous slide, I talked about indirection, like when we retrieve an absolute address and we then effectively have an indirect call. But the one problem is that some recent attacks, such as Spectre v2, which affects many existing CPUs, in the mitigation for those attacks require that we have we have to use more expensive indirect calls. We have to use some workaround for that called red polling. So that impacts the PIC model because now all indirect calls are going to be more expensive. And for PIC module, we actually have indirect calls because that's the only way that we can have 64-bit addresses. But if we call some function from our own module, it still doesn't have to be an indirect call. It can be a direct call with a 32-bit offset. Therefore, optimizations are crucial. So it's very crucial to determine whether it's an internal or external call, and eliminate eliminate an efficient code whenever possible. So we do that at runtime. So whenever we load a module, we do a runtime patching to make sure that we have direct calls whenever possible. And we also perform other optimizations. So for continuous module re-randomization, we use a zero copying mechanism. So imagine that you have several modules running initially. So then the idea is that we're going to create a new virtual address mappings. And this new virtual address mappings are still going to refer to the same physical page. So while we still have some pending calls, all the regions are still going to be mapped. But after all pending calls are done, we're going to switch to the new regions. So we're only going to use new address spaces, and the old regions are going to be unmapped. So it's zero copying because we don't actually copy anything. So in the position independent code is actually crucial here because it also helps us to avoid code modification, because code is still going to be valid at a different base address. We also organize modules into movable and immovable part. Most of the modules is going to be in the movable part. However, the part that is responsible for interaction with the kernel, and it's a very thin part, that part we make immovable because that's just easy to do that, because the kernel itself doesn't move, so and we have to have some logical way to connect to the kernel. So in fact, the immovable part is logically part of the kernel, but something that is still placed inside the module. So in the paper, we discuss how we actually use global offset table. So one difference from shared libraries is that we actually use 4 global offset tables. So to unmap old regions, we use the delayed unmapping mechanism. So we basically want to make sure that we track pending calls in a scalable manner with as little overhead as possible. So we provide some details in our paper, but for the purpose of this discussion, it suffices to know that we need to wrap potential disappearing blocks into MR start and MR finish API calls. So we have so Adelie can perform code transformation, and we have a special GCC plugin for that. So the idea for that, we want to rename the original function from func to funcreal, and that is the perhaps the main part of your module, and this is going to be placed in the movable part. So in the immovable part, we going to create a wrapper for this function. So we're going to call MR start, function real, MR finish, and then we're also going to re-randomize stacks in between, so that whenever we call funcreal, we actually have some random stack. So now the kernel can just kernel can directly use function. So this this address doesn't change because it's in the immovable section. So it can directly reference that address. So for the stack randomization, we maintain a log-free list, and we do it for each CPU to avoid contention. Also, since an attacker may attempt to hijack the return address, we encrypt the return address with the key, and because the attacker doesn't have an easy way to get this key, even if the attacker somehow manages to insert some address, that's most likely going to be invalid because the attacker doesn't know the key. Therefore, that will just contain some garbage. So we evaluate Adelie using a server with 20 cores and Intel E1000E 1 gigabit Ethernet NIC device. We also have the NVMe storage on our server, and we connected to a load generator which also has the E1000E 1 gigabit Ethernet NIC device. We first evaluate NVMe, and we evaluate how we perform on the micro benchmark, which continuously read from the NVMe device. So in this micro benchmark, we also so we don't see any significant difference whether we use stack randomization or not. So the only difference that we observe is that CPU usage slightly increases as we start to use smaller re-randomization periods, such as 1 millisecond. In the next test, in addition to re-randomizing NVMe, we also re-randomize the NIC driver. So we use the MySQL test, and as you can also see, no significant difference whether we use 1 millisecond or 5 milliseconds. Finally, we also run Apache, which additionally re-randomizes several extra modules. So here you can see that for smaller blocks like 512 bytes, you can see some gap, but this gap almost completely disappears like once we go to 20 milliseconds, and 20 milliseconds is still more than enough for continuous ASLR. So all these previous tests are IO bound. However, it's unclear how we can, like, what kind of performance overhead we should expect in the worst case scenario. So we created a special test which is a CPU bound. So we created a dummy module with just one ioctal, and this ioctal is continuously called from a program while this module is being re-randomized. So as you can see in our test, the overhead is still reasonable. It can go up to 4 to 6%. Of course, it's now more visible, but it's still reasonable. Thank you. Adelie source code is available on our website, which you can see on the screen.